In today's video, we're going to be looking at logarithms. They're also called logs for short. Logarithm functions are basically just the inverses of an exponential function. Okay, what do they look like? Well, the way that we write logarithms is like this. Log A B is equal to C. Okay, this is the main part that I want to look at right now. Log A of B. A is called the base. B is called the argument of the logarithm. Okay. What does this function mean? What does it do? What this function says is it's asking what power I have to raise A to in order to get B. So it's asking what is the value of C such that A to the C is equal to B. So the base is the base of that exponential. And B is the number that I want to end up with when I raise A to the certain power. Okay? So that's what a logarithm means. Log base A of B is asking what power do I need to raise A to? What is this power C that I need to raise A to in order to get that value of B? Okay, so for example, let's say I was asked for log base 3 of 81. Okay. Log base 3 of 81, okay, we'll call our answer x. It's asking what do I need to raise 3 to in order to get 81? Well, if I do 3 to the power of 4, I get 81. So the answer to this is 4. Like I said, logs and exponential functions are actually inverses of one another. Okay? Let me draw out a quick graph for you. If you remember, I'll take the value to be a greater than 1. When I drew the exponential function of f of x is equal to a to the power x, this is what that function looked like on a graph, okay, when a was greater than 1. It turns out, and if I go ahead and dot in the line for y is equal to x, that the graph for log base a of x is just the inverse of a to the x. Okay, these two functions are inverses of one another. Okay, why is that? Well, let's think about it in terms of inverse functions. Okay, if I do log base a of a to the x, okay, that's asking what power do I need to raise a to get a to the x? Well, obviously, the answer is x. Okay. Same way the other way around. Okay. If I take a to the power log base a of x, log base a of x is asking me what power do I need to raise a to get x. And I'm then raising a to that power. So if I've basically asked what power I need to raise a to get x, and then raised a to that power, I must have x. That tells me that regardless of which way round I put these functions, I get that f of g of x is equal to g of f of x, which means that log base a of x and a to the x are inverses of one another. Okay, where a is just some number that is either greater than 1 or between 0 and 1. Okay. I will look at more graphs as we go through this topic, but for this particular one here, I looked at a being greater than 1. Remember, when we drew the graph of a to the x, where a was between 0 and 1, that graph was actually flipped in the y-axis, and then it would be the mirror image of that graph in y equals x to get the graph of log base a of x for a is between 0 and 1. In this next set of examples, I'm going to go between exponentials and logs. So let's say I've got 4 to the 3 is equal to 64. Okay, I know that that's true. Can I write that as a log? Well, yes, I can. Okay, I take log to the base of my exponential. My argument is the number that I ended up with is equal to the power. Okay, so log base 4 of 64 equals 3. How about if I do 1 over 5 squared is equal to 1 over 25. Okay. How do I write that as a log? Well, same idea again. My base would now be 1 over 5. My argument is the number that I want to end up with, and the power is the answer. Now let's say I wanted to go the other way. Okay, so let's say now I had log base 4 of 1 over 16 is equal to negative 2. That tells me that 4 to the negative 2 is equal to 1 over 16, which we know is true. And one final one, let's say we've got log base 5 of 125 is equal to 3. Well, that tells me that 5 to the 3 is equal to 125. So we can go between exponentials and logs and write them as one another. The reason that we have done this is because any time that you are given a log, you can 100% use your calculator in order to solve it. There is a log button where you can change the base and the argument and just solve it on your calculator. So you can go ahead and do that. But if you are ever given a log, one of the easiest ways to solve it is to change it to an exponential. So now let's say that I want to solve log base 2 of 32. So I want to know what this equals. Well, it's not easy to see what it would equal without actually writing it as an exponential. I'm looking at the power that I need to raise 2 to in order to get 32. So if I see how many times I have to multiply 2 by itself to get 32, I would get 2, 4, 8, 16, 32, telling me that x is equal to 5. Okay, so I know now that 2 to the 5 is equal to 32, so log base 2 of 32 is going to be 5. Okay. Same thing again if I try to solve log base 5 of the square root of 5. Okay. That tells me I'm looking for the power I have to raise 5 to get the square root of 5, which obviously is 1/2. So log base 5 of the square root of 5 is just 1/2. So whenever you get a log, one of the easiest ways to solve it is just to go ahead and write it as an exponential, and then you can see what you have to raise the base to, whatever power it might be, in order to get the argument. Like I said before, there are two basic graphs for a log function. Okay, we've already looked at one of them, which I said was when your base a is greater than 1. So let's say you've got log base a of x. This is what our function is going to look like. And this is where a is greater than 1. We said that the graph would look something like this. Now I know the inverse of this is a to the x, where a is greater than 1. And I know that that graph goes through 0, 1. Now remember, the inverse of a function has to go through the point where I've switched the x and y coordinates around, telling me that this graph must go through 1, 0. That makes sense, okay? When x is equal to 1, I'm looking at what power I have to raise a to in order to get 1. Well, any a to the power 0 is going to give me 1. So log base a of 1 has to be 0, because a to the 0 power is always 1. So 1, 0 is going to be a point it goes through. Another point I know it goes through is a1, okay? If I look at what log base a, where x is equal to a, I'm looking at what power I have to raise a to get a. Well, that's just 1, okay? A to the 1 is a. So I know that that is the case. What about domain and range for this? Well, our domain, if we look at this, is 0 to infinity, okay? That y-axis is an asymptote in exactly the same way that the x-axis was an asymptote for a to the x. So I can go closer and closer and closer to 0, but I'm never actually going to reach it. So that is actually a vertical asymptote. And I can go all the way up to infinity. How about the range? Okay. Well, I can get any function value I want out of this, okay? I can raise a to any power that I want to get x. So my range is actually all real numbers. This should show you exactly what we said about inverse functions. Remember that I switched the domain and range for an inverse function. So for a to the x, my domain was all real numbers and my range was 0 to infinity. So now my domain is 0 to infinity and my range is all real numbers for this log function. Like I said, my vertical asymptote here is just x is equal to 0. It's that y-axis. Okay. When we look at transformations of these graphs, that asymptote will shift if you shift left and right. If you shift your graph up and down, that asymptote doesn't move. Okay? It's only if you shift left to right that that asymptote is actually going to move. Let's quickly look at what it would look like if I had a was between 0 and 1. Okay, and I'm looking again at f of x is equal to log base a of x, where this time a is one of those numbers between 0 and 1. What does that graph look like? Well, it's just going to be, if I took the graph of the exponential function a to the x, I took that graph where a was between 0 and 1, and then I flipped that graph in the line y is equal to x. This is the graph that I get. Okay. What points does this go through? Okay, it goes through the point 1, 0, again because a to the 0 is going to equal 1, and it also again goes through the point a1 because a to the 1 equals a. Okay. Exactly the same properties as the previous graph holds. So our domain is still 0 to infinity because I have that vertical asymptote at x is equal to 0. And my range, again, is all real numbers. Okay. Now, let's say I wanted to sketch the graph of f of x is equal to negative log base 1/2 of x plus 3. What would this look like? Well, I'm taking the graph of log base 1/2 of x, and what am I doing to this? I'm going to shift it to the left by 3 units. And then I'm going to end up flipping it over the x-axis because of this negative. Okay. If the negative was in front of the x, I would flip over the y-axis, but my negative is out the front of the function, meaning that I flip over the x-axis. Okay, it's going to deal with it vertically. So if I take my graph of log 1/2 x, it's going to resemble this graph here. I'm shifting it left by 3 units, meaning that this point 1, 0 is going to go to negative 2, 0. So this point is going to end up over here at negative 2, 0. My A1 point, okay, that would be 1/2, 1, again is going to shift to the left by 3 units, ending up at negative 5 over 2, 1. And then it's going to be flipped in the x-axis. Okay, that means that that point on the x-axis is going to stay where it is. So negative 2, 1 is going to stay where it is. This point is then going to flip, going to negative 5 over 2 and negative 1. So my graph will end up looking like this, where I go through negative 2, 0, and negative 5 over 2, and negative 1. And I'm going to end up with this asymptote. Remember, I have shifted to the left by 3 units, meaning that my asymptote is also going to shift. So my asymptote is now at x is equal to negative 3. So there are many examples that you can do depending on which of our 2 log graphs you have taken, depending on what your base value is here. Here we had a base value that was between 0 and 1, so we were shifting this graph here with all of its asymptotes, etc. Or you could end up with a graph where you had a was greater than 1, so if your base is greater than 1, then you are shifting this graph here, but it will work in exactly the same way, whether you're shifting up, down, left, right, etc. Just remember your asymptote is only going to shift if you are shifting left and right. Shifting up and down is not going to affect that asymptote. What does that mean for our domain and range? Well, here, our range is still going to be all real numbers, okay? For either one of these graphs, no matter how you transform them, your range is still going to be all real numbers. No matter if I shift it left, right, up, down, stretch, compress, whatever I do to it, my range is still going to be from negative infinity to infinity. No matter what I do to this graph, that is still going to be my range. What about my domain? Well, my domain for either value of a, whether it's between 0 and 1 or greater than 1, my domain started at 0 to infinity. But that domain is going to change if you shift left or right because that asymptote shifts. So here our domain is from negative 3 to infinity. If I would have shifted right, so if I would have had a negative 3 here, it would have shifted to the right, meaning it was 3 to infinity. So just kind of keep in mind when you do these shifts, or if you do any kind of reflection over your y-axis, then that domain may change. If you do a shift over the y-axis, then obviously your domain would change not only with a shift left and right, but you would then be going from negative infinity up to your asymptote, not just from your asymptote to infinity. So keep that in mind if you do have that shift over the y-axis, where you've reflected over the y-axis, then of course your domain will also change with that. But otherwise, your range is always going to remain the same regardless. It's just your domain that's going to change when either you shift left or right or reflect over the y-axis. Okay. Let's do one more quick example of the domain and range. So let's say I'm looking at the domain and range of f of x is equal to log base 3 of x plus 2. Okay. My range, like I said, regardless of the function, regardless of what I've done to it, is still going to be all real numbers. My domain, what am I doing here? Well, I start out with log base 3 of x, and then I'm shifting that graph to the left by 2 units. Okay, so I start out with a domain of 0 to infinity, shifting that to the left by 2 units. My asymptote's going to shift to the left by 2 units, meaning that my domain is negative 2 to infinity. Okay. One more, let's do the domain and range of f of x is equal to negative log base 1/2 of x minus 2. Okay. Now what I'm doing here is I'm shifting to the right by 2 units, and then I'm flipping over the x-axis. Well, that flipping over the x-axis doesn't change my domain at all. So my domain, because I've shifted now to the right by 2 units, is going to be 2 to infinity, and my range stays at all real numbers.